Now we will determine electric potential energy stored in a charged conductor or in a charged capacitor. When a conductor or a capacitor will be charged, then either we will be continuously giving electrons to it or will be taking electrons from it. Say we are making it positively charged, it means we are taking electrons from it. When we will take out an electron from it, it will gain a positive charge of 1 unit, and because of that positive charge attained by it, the capacitor or the body will oppose the withdrawal of second electron from it. It means to withdraw second electron from the body or the capacitor, we will have to work on it. Similarly, if we have withdrawn 2 electrons, then the body or the capacitor will be having 2 units of positive charge, and now to withdraw third electron from the body, we will have to work more on the capacitor or the body. It means in charging the body, always we will have to work on the body. This work done by us on the body to charge it will get stored in the body or in the capacitor in the form of electric potential energy. Now we will determine the expression for this electric potential energy. We know that electric potential is work done per unit charge. It means electric potential into charge can give us the work done. If charge given to the body raises its potential V, then by the product of Q and V, we can find out the work done on the body, and that work done will get stored in the body in the form of electric potential energy. And we know that the product of two quantities is always obtained by the area between the horizontal axis and the curve for those two quantities. Say here I am plotting electric potential against the charge given, then we know that electric potential is directly proportional to charge because C is constant. Hence the graph between charge and electric potential will be a straight line moving away from both the axes. At Q is equal to 0, potential will be 0, and at charge equal to Q, electric potential will be V. So the work done in charging the capacitor or body will be given by this area between horizontal axis and the curve, and we see that this figure is a triangle, and area of triangle will give the electric potential energy. So electric potential energy is stored in charged body or capacitor equal to area triangle OAB. This is equal to half, base is OB and height is AB. This implies electric potential energy U is equal to half, OB is charge Q multiplied by AB is electric potential V. So electric potential energy stored is half QV. If charge Q given to the body raises its potential V while capacitance of the body is C, then V will be given by Q by C, or you may say Q is equal to CV. If you will write Q is equal to CV, then this expression will become half CV square. Or if you are writing V is equal to Q by C, then this expression will become half q square by c. It means the electric potential energy stored is half qv or half cv square or half q square by c. But nowadays this expression is obtained using calculus. It means we will use calculus to obtain this expression for electric potential energy stored in charged body or capacitor. Say again, we have given charge q to the body having capacitance C such that its potential rises to q upon C. If during the process of charging the body at any instant charge on body is q dash, such that its electric potential V dash is equal to q dash by C, because charge is q dash, so rising potential will be q dash upon C. Due to charge q dash, potential on body is V dash, and at this potential V dash, if we are further giving a charge dq dash to the body, then dq dash being so small that changing potential due to dq dash is negligible, it means we can assume that charge dq dash is given to the body at electric potential V dash. Then work done in further giving charge dq dash to the body dw is equal to electric potential energy stored in giving charge dq dash, that is du. This is equal to V dash into dq dash. Now V dash is q dash by C, so energy will become q dash by C into dq dash. Now work done in giving the total charge q to the body, that is total electric potential energy stored in giving charge q u is equal to integral du, limits from 0 to u, equal to 1 upon C being constant will be outside the integration, integral q dash dq dash and limits from 0 to q. Now integration of q dash with respect to q dash will be q dash raised to the power 1 plus 1 upon 1 plus 1, limits from 0 to q. This is equal to 1 upon 2c, and this will become q dash square, limits from 0 to q. So this will become 1 by 2c, and upper limit means q square minus 0. This is equal to half q square by c. Thus electric potential energy stored in capacitor or charged conductor, u is equal to half q square by c is equal to, if q by c is written as v, then half qv, and if q is written as cv, then c square v square divided by c, that is half cv square. In this way, we can determine the electric potential energy stored in charged capacitor. For a spherical body of radius r, its capacitance C will be 4 pi epsilon into r. So electric potential energy stored in it will be half CV square. Half C is 4 pi epsilon into r multiplied by V square. And hence the potential energy stored per unit volume of the body, that is electric potential energy density within the body. Small u is equal to capital U upon volume, and capital U already we have calculated, half 4 pi epsilon r into capital V square divided by volume of sphere 4 by 3 pi r cube. This is equal to 3 by 2 and pi will get cancelled. Epsilon V square upon r square. So it will become 3 by 2 epsilon V square upon r square. Now for a parallel plate capacitor, capacitance C is given by epsilon A upon D. A, area of each plate, and D, distance between the plates. So potential energy is stored in parallel plate capacitor, half C will be epsilon A upon D into rise in potential square. If we want to find out electric energy density, that is electric potential energy stored per unit volume of a charged capacitor, then that will be U divided by total volume of capacitor. This is equal to U is half epsilon A V square upon B, and now the volume of capacitor is having two parallel plates, each of area A and distance between the plates is D. So the volume will be area into distance, that is A into D. It means A into D will be volume. A will get cancelled and here it will become half epsilon V upon D whole square. And we know that potential difference per unit distance is electric field. Electric field within the plates of capacitor. So half epsilon E square. It will be the electric potential energy density within the plates of a parallel plate capacitor. And U is equal to half epsilon E square will be the expression for electric energy density within the electric field produced by electromagnetic waves. Now we will prove that energy stored in the combination of capacitors is equal to the energy stored in their equivalent capacitor. Say we are taking a number of capacitors of capacitances C1, C2, C3 so on connected in series across a source establishing a potential difference V across them. In case of series combination, charge on the plates of all capacitors will remain the same. So we will use the formula of potential energy stored in which charge and capacitance are used, and that formula is half Q square by C. So energy stored in all the capacitors is equal to energy stored in first capacitor half Q square by C1 plus energy stored in second capacitor half Q square by C2 plus energy stored in third capacitor half Q square by C3 plus so on. This is equal to half Q square will be taken as common, so Q square by 2 will come outside and it will give 1 upon C1 plus 1 upon C2 plus 1 upon C3 plus so on. And we know that it is 1 upon C, so this expression will become half Q square by C. Q will be the charge drawn by combination from the source, which will also be equal to the charge drawn by equivalent capacitor when connected across the same source. So Q square upon capacitance of equivalent capacitor will give the energy stored in equivalent capacitor. So we can say that this total energy stored in combination is equal to the energy stored in equivalent capacitor. Similarly, for parallel combination, if we are considering again that a number of capacitors are connected in parallel across a source of potential difference V, such that the combination draws a charge Q from the source, then equivalent capacitance will be given by the sum of capacitances of individual capacitors, while in this case potential difference across individual capacitors will be same as the potential difference across equivalent capacitor. It means in this case potential difference will be same. So we will use the formula in which capacitance and potential difference is used for calculation of energy. So total energy stored in combination, U equal to energy stored in first capacitor half C1 V square plus energy stored in second capacitor half C2 V square plus in third half C3 V square plus so on. Half V square can be taken as common, so it will give half V square into C1 plus C2 plus C3 plus so on, and this will give us the capacitance of equivalent capacitor. So this is equal to half C V square. V is the potential difference across equivalent capacitor, C is capacitance of equivalent capacitor, so half CV square will be the energy stored in equivalent capacitor. Thus we can prove that the total energy stored in combination of capacitors is always equal to the energy stored in their equivalent capacitor. Now we will determine the force between the plates of a charged capacitor. We know that the plates of capacitor have equal and opposite charges, and we know that the opposite charges always attract each other. So the two plates of a charged capacitor will always attract each other. Now we will determine an expression for the force experienced by a plate of capacitor due to the another plate. Since every action has equal and opposite reaction, whatever force will be exerted by one plate of the charged capacitor on other will be exerted by the other plate on the first plate. So we are determining, say, the force on second plate due to the electric field produced by the first plate at the position of second plate. Since a charge placed in electric field will always experience a force charge into magnitude of electric field, so the electric field at the position of second plate due to the charge on first plate will be E1 equal to sigma upon 2 epsilon, because electric field due to a thin metal sheet at a point near it is sigma upon 2 epsilon. Sigma means charge per unit area only, plate 1, so it will become Q upon 2 epsilon A. Since the second plate is placed in this electric field, so the force on second plate towards the first plate will be F2 equal to magnitude of electric field, that is E1, multiplied by charge on second plate, that is Q. E1 means Q upon 2 epsilon into A multiplied by Q. This will give half Q square upon epsilon into A. Also, it can be written in terms of electric field between the plates of capacitor. We know that electric field at a point between two equally and oppositely charged plates, E is sigma by epsilon, that is Q upon epsilon into A. So Q upon epsilon into A can be written as electric field between the plates of capacitor, and then the expression of force between the two plates of a charged capacitor will be half Q into E. So thus the same force will be exerted by the second plate on the first plate. Thus attractive force between plates of a charged capacitor F will be force exerted by first plate on second, or force exerted by second plate on first, that is half Q square by epsilon into A equal to half charge on each plate multiplied by electric field between the plates.